LoRA, qLoRa, quantization, parameter efficient fine tuning, all things I know I should be doing, but I don't know how. Well, I've got you covered. Hello everyone, and welcome back to my channel. As promised, this is going to be a full-on demo of fine-tuning using qLoRa. I'll be using Google Colabs for this demo. I'll also be covering GPUs and going over some of the basics of what GPUs to use so you know what GPU you should use for your own fine-tuning. If you like this, please like and subscribe. That's going to help me out a lot. Now, to start, let's cover the basics of parameter efficient fine-tuning. What is parameter efficient fine-tuning, or PEFT? PEFT is an approach to fine-tune large pre-trained models without updating all their parameters, which saves compute, memory, and time. Why do we need PEFT? Well, fine-tuning billions of parameters is expensive and requires lots of GPU memory. PEFT updates only a small subset of parameters. This allows fine-tuning using fewer GPU resources, making it cheaper and faster and easier to store and share. That brings us to LoRA, which stands for Low-Rank Adaptation. LoRA is a form of PEFT. Instead of updating the full weights, LoRA injects small trainable adapter layers into the model. Only these small adapter weights are updated during training. The original model stays frozen. This brings us to quantization. Quantization shrinks the number of bits used to store and process numbers in a model, so it takes up less memory and runs faster, often with only a small hit to accuracy. For LLMs, weights are stored in 4 bits instead of 16 or 32 bits. Think of this as comparable to saving a photo at lower resolution. When you save a photo at lower resolution, the image becomes smaller. It might have less detail, but it loads faster and uses less storage. Finally, this brings us to qLoRa, or Quantized Low-Rank Adaptation. qLoRa combines quantization and parameter efficient fine-tuning using LoRA. It allows you to fine-tune very large models, aka 7 billion, 13 billion parameters, on a single GPU with as little as 24 gigabytes of RAM, which, as you'll see in our demo, is important. Before we can actually start training the model, we have to go to Hugging Face here and acknowledge a license, accept this license, so we can use it. Let's go ahead and do that. Acknowledge the license for Gemma and authorize. I'm already logged in here. My account. And let's go there and there. Let's do that. And we are good to go. I forgot to mention the page where we need to acknowledge the license was the actual model card page, which will be in the YouTube description below. Okay, since we're on Hugging Face here, we also need to create an access token in order to use the Hugging Face services here. I will go ahead and do that. You just go to it by going to Settings, Tokens. To create an access token, we actually need to give it write access for this project. So let's go ahead and do that. I'm just going to call it Gemma Demo and create that token and copy this. I'm going to delete this before I release this video, but make sure you copy it. Okay, now we're going to go to Google Colab. So go to colab.research.google.com, and I'm already here, and I'm going to create a new notebook here. The first thing I'm going to do is create that access token. If you go here to the right to your secrets, you have to create one called HF_token. I already have one here, but I'm just going to copy over and copy that one that I did before. And make sure you do that because you can't do anything without that. Okay, next we can go ahead and install our libraries. I'm just going to copy and paste this here. And let's go ahead and run this. This will install PyTorch and the Hugging Face Transformers library and the Datasets libraries and a few more that we need here. So this might take a little while. That finished. Okay, so in order to actually do anything, we have to actually restart a session here, which I will do. Yes. And that should refresh it. I also forgot to mention here that I have the library, the flash attention. I'm not doing that right now. Flash attention is the method that significantly speeds computation up and reduces memory for the transformer models. If you're using a GPU with Ampere architecture, you can take advantage of this. Right now, I'm just going to leave this commented out. Okay, next, let's go in and actually log into Hugging Face. So I'll paste the code here. This will grab our Hugging Face token, which we copied earlier, and log in. And we have to grant access, yes, so do that. And as long as there's no error that comes back, we should be good. Actually, did that run? Yes, that ran. Okay, we are good. Okay, I'm just going to show you here the data set that we're going to be loading. We're loading this from Hugging Face. There are data sets here. This is a text-to-SQL data set, which is, of course, the model we're going to be fine-tuning for. We're going to fine-tune our model to give us SQL from a text prompt. So if you see in here, we have a prompt here, description of this stuff and what this is actually going to be doing. And we have the SQL context and the actual SQL and a little bit of explanation of what this SQL statement is doing. So this is what we're going to be using. Okay, let's go ahead and start loading the data set here in our workbook. So I got to import the Datasets library here, and now let's actually load it and randomly pick out a few of the entries here. It should be reading. And we are good there. Okay, we have our data set loaded. Is that enough? No. We need to actually convert this to something that we can use. Now, we're going to be using the Hugging Face Transformer Reinforcement Learning Library. And for that, we need to have this data set formatted as a conversation. And I will show you that next. Okay, next, let's go in here and write some more code. Let me just paste this in and explain it to you. This is going to be our prompt. As I said, we need to convert this data set to a conversation. So it's going to have the system prompt, the user prompt, and then a response, what the assistant's going to say. So that's the format we need. So here we're saying we're giving the system prompt as you are a SQL query translator. We are giving a user prompt all the time. As example, given the user query and the schema, and give us the response back in SQL, and we're going to be building this up on our data set. So let me go ahead and run this, and I will continue in a second. So that should be good. Next, let me just paste this code here and explain this to you in a second. Okay, so what we're going to do is we're going to take our data set, and as I said, we're going to convert it to a conversational prompt, and we're going to split the data set into our training samples and our test samples. And I'm just going to output one here just to show you what it looks like and try to explain this. So here we go. We've picked one randomly here, and as you can see, it has our prompt here. We've actually commented out the system prompt for now, but you see as the user, we have our user response. So what we're saying is giving the query and the schema generate the format SQL data, which we're going to build up from our data set from the SQL context. So as an example, given the user query here and the schema and query, we're going to be giving back a nice formatted SQL statement. So the query will be something in a text format. So that's the prompt that we want the user to have, because that's what we want the model to do, convert text to SQL. So I hope that makes sense. I probably didn't explain it that well, but this is what we're going to be doing to train this model. Have you noticed something? I forgot something. And what is that? It's the runtime environment, of course, what GPU we're using. So that's what I'm going to talk about now, specifically comparing the T4 and the A100. The T4 GPU was released in 2018. Its RAM is 16 gigabytes, which will be an important consideration for our demo. Its purpose? Cost-efficient inference and some light training. The A100 GPU, the Ampere architecture, was released in 2020. Its RAM, significantly more, 40 gigabytes. Its purpose, high-performance AI training and inference. The A100 has BF16 support, BF16 meaning brain floating point 16. This BF16 support will allow us to do flash attention. If you remember from our setup, we disabled that. The A100 is 4 to 5 times faster for inference and 10 times faster for training. And if you look at the cost though, the A100 is around $3 to $4 an hour versus 35 cents an hour for the T4. And again, these are just estimates and they could change over time. Okay, to save a little bit of time, I've gone in here and added some code to our notebook. And first thing, as I mentioned, let's go into our runtime and choose our runtime type. Now I have all these options because I bought some credits from Google Colab here. But the T4, this should be free. So if you're on a free account, you should be able to select it. And I just saw the T4 is a lot cheaper, but we do have some RAM considerations. So we'll take that into consideration compared to the A100. But let's go for the T4 right now. I have a bit of code here just to confirm that this is a T4 and it's a Tesla, not the NVIDIA on Google here. And as you remember, the BFloat16 support is not supported on the T4. The brain floating point 16, remember at the very start, we had this commented out. This is the flash attention. So we cannot do flash attention on the T4. But if you were running this on the A100, then you could do this flash attention. Okay, another thing I want to point out is we actually have to install Torch. If you did PyTorch on a GPU, you have to make sure this has CUDA enabled. I think I already installed it. Nope, it's actually going to go in there and do this again. So I'm running this, and I'll come back to this in a second. Okay, that finished. Next, we have to also install the BitsAndBytes library. This will allow us to do quantization. Looks like I need to install it. So I'll install that and come back. That one's done. Another thing I want to mention is this workbook. I'll put it in my GitHub account. So if you want, you'll be able to grab that from the YouTube description. Next, we actually have to create our model. We are going to be using from Hugging Face the Gemma 1 billion parameter model. You could use a larger one, but for my training purposes, this is still going to take a while, the 1 billion parameter. So I'm going to use that one. It'll use the auto model for causal LM, of course. And remember, we can't do brain floating 16. So it's going to pick float 16 for the torch configuration. We can't do flash attention as well. It's going to try, but it can't. How it sets up the model will be auto. These are our quantization parameters. Let me explain this a bit. So remember quantization, we're going to be storing the weights as 4-bit instead of 16 or 32-bit. So that's what we're saying here, load in 4-bit. That's what that means. The two-stage, so we're using two-stage quantization. That's what the use double quaint means. and a 4 normal floating point quantization. And of course, we're saying we're using 4-bit for quantization. So those are the parameters we need to pass in order to do qLoRa fine tuning. And of course, we also have to create our tokenizer here for the instructions, use that in the process here. So go ahead and run this cell. Okay, that finished. Now for our parameter efficient fine tuning library, we can finally state our LoRA config. So this is the LoRA config that we're going to use. Remember, this is low-rank adoption LoRA, and we are training the weights and biases. So that's what we could be doing, but we're not doing the biases here. That's why the none is there. These parameters I had to kind of adjust because of the RAM limitations. So you have to play with these numbers. But I got these numbers, of course, off the internet. The LoRA alpha, that's kind of like the scaling factor for the updates to the adoption layers. Think of it as how much to amplify the learning weights before applying them to the frozen models. And the dropout of 0.05 means the dropout probability of the LoRA layers during training. The task type, causal LM. This is left to right language modeling, which is kind of like the GPT style, which helps with the LoRA here as well. And we have to save the head and embed tokens. And so we'll just go ahead and define that. And let's also install this library, the TRL, the Transformer Reinforcement Learning Library. Let's define that as well. That's what we're using this here. I think I already installed it. And now we can go to our supervised fine-tuning config file. Okay, when we actually do the fine-tuning, we're going to save our weights file, and that's going to be in an output directory, Gemma text to SQL. For supervised fine-tuning, epochs, remember that's the number of rounds we're doing here. We're doing it as 3, pretty standard. This is the number I had to play with, the max length, which is the batch size. I set this as 512. You might want to play with it, depends on what you're running this on, but for the T4 with 40 gigabytes, I read up and I think I saw 2048 somewhere, but I'm changing this to 512 and this seems to work for me. The rest of this is pretty straightforward. I got a lot of this off the internet, of course. And so let's go ahead and just run this. We are good there. This is another thing I got. I read up in order to save on memory. Try running this. And now we should be able to define our actual trainer that will do our supervised fine tuning for us. So let's go ahead and run this. Hopefully this works. Yep, it is initializing. That's great. All right, and now the moment of truth. Let's see if we have enough memory. Actually, one other thing I read up on is this parameter here, a PyTorch. This will free up some memory. I grabbed this. Again, this will be on my notebook, so you can grab this. And let's also free up some memory. And let us start the training. If this goes, we'll let this run, because on the T4, this might take a while. But let's see if it works. And it is. Amazing. So I'm going to let this run for a bit, and we configure this to output the steps. So let's let this run for a bit. You can see how it's progressing, and it might take a couple hours, but you'll see the training loss and the steps. I'm going to let this run, and we'll come back and test it. Okay, I am back, and as you can tell by the color here and by my screen, it's around 8:30 p.m. The training is complete, and looking here, that took almost 3 hours to get through the 3 epochs on the T4, but it's done, and we called the trainer save model. So I just opened up the file explorer here. You can see that it's been saved. As you know, we don't actually save the model, we save the adapters. You're only training the weights and not the full model. So if we wanted to take this model and use a different inference provider, maybe LLM, we'd actually have to take the weights and merge it with the model itself so we can use it. I'll just show you that code here. I'm not going to run it. I'll tell you why. So first, I'm actually going to delete this model and the trainer to free up some space so we can actually infer it. Oops, I already deleted it. Sorry, I already clicked this and done it. So that's why you get this error. Okay, so this is the code that we would use to actually merge it. The problem is this would take around 30 gigabytes of memory. And if you remember, the T4 had around 40 gigabytes. And Torch itself, PyTorch, I think uses around 20 gigs or 25 gigs. So you're not left with a lot of memory. So if you actually want to merge this, I don't think you can use the T4. You would have to use the A100, which would cost you money. So I'm not going to do that. And we're just going to infer it anyways from what we saved here. So that's what I'm going to do next. Okay, next we are actually going to load our model from the saved weights here. And we are just going to run this, again, just using pretty much the same variables that we've done before in terms of attention, eager, but it's not going to do that. And we have to load up a tokenizer as well. So let's run this. This will take a few seconds. That's done. Okay, next, we're going to randomly use some of our test data. Well, first, we're going to create our pipeline for text generation using our fine-tuned model and passing in the tokenizer. And then we're going to get a sample from our test data that we declared earlier and just pick a random variable. And I'm just going to print this to get our prompt. And this is what we're going to run. And we will look at the data and compare it to what we expect. So let's do that next. Oh, I have an error. Okay, I have a confession. I made an error. I read some other instructions and just followed along what they were doing, and I see this was not working. Once I called the inference on my fine-tuned model, it was not giving me output. I think it's best to learn from mistakes, and that's why I'm keeping this in here. And I'm going to show you what I did to fix it and why the error happened, and we will continue. Something happened in my fine-tuning process. I did some debugging and did some reading up and made some changes, and I'm going to show you what I've done. First off, when you're doing the fine-tuning with the model here and the tokenizer, you have to make sure these are the same. I just made a change. I'm actually using instead of the base PT, which is the pre-trained base foundation model, I decided to use the instruction tuned model, which is much better for prompts and responses. I also read for what we're doing, you probably should do on the base foundation to fine tune, but this saves time. Time meaning you don't have to do as many epochs when you're doing the fine tuning. So I'm just doing this as IT. And you just have to make sure when you're creating your model and your tokenizer, they both use the same tokenizer, meaning whatever model you're putting in here uses the same tokenizer. But I also read these are the same tokenizers because they're both based on the same foundation model. So something might have happened just in my fine tuning, but I went ahead and I fine tuned the model again, and we're going to try it again and see if this works. Okay, as you can see here, I've fine tuned this model again. The epochs here, I'm just doing it as 2 just to save time. Now it was less than 2 hours. So I've gone ahead and done that, and I ran it and scroll down here. And of course, I've already gone in here and deleted the model and the trainer after we did the training. So that's done. This here is just the merging, which I already talked about. Now let's go ahead and load our fine-tuned model again. I've just set the tokenizer as to load it from the same model just to make sure. So go ahead and run this. And I've also included a basic test. This is when I was debugging, I saw that even just doing a simple base test, nothing to do with text to SQL, I was not getting any generated output. So that's where I found out that my fine-tune model, something was broken. I've included this. Again, this is all going to be in the workbook, which will be available from my GitHub repo. I'm not going to run this because I saw that this worked. Now we're going to reload our pipeline. So I will go ahead and run this. And I'm going to load up some data. Again, this is what I already showed you that we're going to use to put into our prompt. So given the user query and schema, and which has the schema here and some text. What is the average release year of songs in the folk genre? That's our text that we want to convert to SQL. So done that. This is what we're going to test. I've also included some test code here to inspect the pipeline. So this is where we actually create our prompt. I think I forgot to talk about this before. Make sure you have this stop token defined here. This is important. I'm just going to output what we're actually going to send to our pipeline. You can see we have our token keywords here that we're going to instruct the LLM to actually complete this. So going in here, what is the average release dates? This is what we're going to send to the pipeline. So let's go ahead and do that and see if this generates our output and compare this to what we get. And here we go. This is it. This is the original answer that was in our test data set. Select average song year from songs. And this is what we have generated. It looks a little different, but it seems to be working. So we are good. We completed our fine-tuning of our model and ran it, and things look good. So that's great. Okay, that concludes this demo. As I said, I think it was important to leave the error in because errors happen, and I wanted to include that just to reinforce the learning about the model, the tokenizer, and I hope you actually go ahead and try doing this yourself. And please let me know if you do, how it went, if you used the foundation model or did you use the instruction set model to do the fine tuning on. Go ahead and do that and let me know. And I hope you got something out of this. I enjoyed making it and I will see you the next time. Bye.